okay? Okay. So first of all, I'd like to thank the organizers for giving me the opportunity to give this talk, which is not completely related to transport. It's slightly off topic, but there are some connections to dynamics and maybe transport. I'm going to try to point out in this case. So this talk is about an ongoing work which I'm doing with Jacopo Vitti from the IIP and Gabor Takács from Budapest University of Technology. And it's about ground states of massive quantum field theories in 1+1 dimension, for which Cardy recently gave an ansatz in terms of conformal boundary states. And I'm going to talk about this left-right entanglement entropy as well, which is a new kind of entanglement entropy, which is defined between the CFT left and right movers. Okay. And actually, I'm going to use this quantity to verify Cardy's ansatz. Okay. So let's I'd like to give some general introduction about the space of quantum field theories, because I'm going to talk about quantum field theories in 1+1 dimensions. So, like for me and other people, like quantum field theories, you can handle them as some renormalization group flows or renormalization group trajectories, which has some non-trivial fixed points, which are described by conformal field theories. So for me, like massive quantum field theory and renormalization group trajectory or RG flow and relevant perturbations of conformal field theories, they're gonna mean the same. And like the question is like how to characterize a general massive quantum field theory. And generally it requires some non-perturbative methodologies. And like in particular, like the ground states are of particular interest. For example, you can ask the question like, what is the ground state energy of such field theories? The ground state is also related to the phase diagram of the system. For example, if you have a regular second order phase transition, you can have some order parameter which is a one-point function of some local operator. So this order parameter is 0, then the system is in disordered phase, and if it's non-zero, it's in some ordered phase. But this depends. I mean, the one-point function, when you calculate, you need the exact ground state. There are other types of states of matter, which and other type of phase transitions, which are not, it's called topological phases of matter, and in these cases, there are no order parameters, but the entanglement properties of the ground state contain information about the state, and then you can characterize different phases of matter. And also, of course, there are other interesting questions. So in this talk, I'm going to talk about 1+1D field theories and massive perturbations of unitary minimum models of conformal field theories. Okay. Just some words about what we know about quantum field theories in 1+1D. So if you have a general QFT, let's say we don't know so much. But if you have some extra symmetry, like conformal symmetry in the fixed points of the renormalization group, then the symmetry is put so strong constraints on the theory that basically you can solve it. So you can, using operator product expansion and conformal invariance, you can in principle calculate any endpoint functions in this case. There are some new developments on the entanglement properties, like real space entanglement properties, based on this replica trick and the twist field calculation. So the in CFT also the real space entanglement entropy can be calculated. Okay, and then if you are not in the fixed point and you lose conformal symmetry, you still can have some very big symmetry, and these models are called integrable models. In these cases, you also can calculate many of the things, like for example the spectrum of the theory and the scattering theory and the scattering phases of the theory. And also finite size effects can be characterized using thermodynamic beta ansatz. In this case, one can calculate one-point functions and form factors, which are matrix elements of local operators between some states. And using these inputs, you can write some formal expansions for any endpoint function, which fortunately converge very fast. So if you know these inputs, usually you can calculate any endpoint function with a very good approximation. And this twist field approach for this form the twist field approach is also worked out in this case because you can calculate the form factors of the twist fields, and using this, you can calculate the entanglement entropy in the ground state, the real space entanglement entropy. And then after I said, okay, we don't know so much in general, but we can use these two inputs as doing some perturbative calculations around these specific points, like conformal perturbation theory or form factor perturbation theory. So, okay, this was my general introduction, and I want to give the outline of the talk. So first, I'm gonna introduce this ansatz for the ground states, which was proposed by Cardy recently, and then I'm gonna explain what is left-right entanglement entropy, and then I will compare the results with numerics, which is called truncated conformal space approach, which I'm also going to explain, and then at the end I'm gonna conclude. So, okay, let's start with Cardy's ansatz. So, like, this is the general problem. We have a perturbation, relevant perturbation of some fixed point, which is, I thought, generally it's a massive field theory. And then we put the theory on a circle with periodic boundary conditions. And these perturbations, they must be relevant. And if you want to respect Lorentz invariance, they also have to be spinless fields of the CFT. So the question is, like, you have this Hamiltonian, and what is the ground state of it? And there are some indications which I'm going to show you soon, that the characterization is somehow related to the possible boundary states of the CFT. And this part of the talk is based on Cardy's paper from last year, Bach, RG flows and boundary states in CFT. So let's talk about these indications. Okay, so first of all, let's imagine that you have your theory, which is defined in 1D, 1 plus 1D. So your theory is defined on a line. And then you cut it to two halves. And on one side, you turn on this massive perturbation. And on the other side, you leave it like as a CFT. So you end up with a model which has an interface. On one side, there is a massive theory, on the other side of the CFT. And now you sit on the CFT side. And then when you see the boundary, what you're going to see, it's a CFT with some boundary conditions. But also from Cardy's earlier work, you know that boundary conditions, under the boundary RG, they flow to some conformal boundary conditions. So based on this, you can say that close to the boundary, like the correlations are similar that of a conformal boundary condition deformed by some irrelevant operator, because let's say in this case you are out of the fixed point, but out of the boundary fixed point, but the boundary condition flows to the fixed point, so it must be some irrelevant perturbation of the boundary fixed point. So this is the first indication that that somehow the ground states of the massive theory might be related to the boundary states of the CFT. The next indication is based on Cho, Ludwig, and Riu's work where they studied the entanglement Hamiltonian. So the entanglement Hamiltonian is defined in a following way. You have your system, and you cut it to two halves. Let's say A and B. You have two subsystems, and then you calculate the reduced density matrix of, let's say, the subsystem A, and then one can write this as some exponential of some Hamiltonian, and people call this Hamiltonian entanglement Hamiltonian. And what they found in this paper, that the spectrum of this entanglement Hamiltonian is the same as the spectrum of a boundary CFT. Namely, this boundary CFT is given by with two boundary conditions. One is free, and the other boundary condition is related, is a specific boundary condition, and it's governed by the perturbation that you are using to get out from the fixed point. And these results that they have is supported by numerics for the Schiffer-Hegel model. And the last indication is based on Cardy and Calabrese's work on quantum quenches. In this paper, what they did, they studied quantum quenches from off-critical models to the critical point. And they calculated correlation functions in this case. So what you do in this calculation, you can do a path integral approach with some initial conditions on the path integral, which should be like the exact ground state of the massive field theory. But instead of that, they used some deformed conformal boundary conditions, and they got very good results which are in agreement with numerics for the X-pi model. So based on these three indications, Cardy wrote the following ansatz for the ground state of the massive field theory. So the ansatz that he proposes is you take the possible physical boundary states of the CFT, and then you take this linear combination with these regularization factors here. And what you have to do is minimize the free energy in large volumes. So this ansatz is valid in large volumes, large system sizes. And these alpha A and tau A parameters, they are variational parameters which are set by the minimization of the ground state energy density in this state. So let's talk about the details of this state. Like the boundary states, the Cardy states in diagonal minima models, they can be written in this linear combination of Ishibashi states. So these S matrix elements, they are the matrix elements of the modular matrix, which describes the transformation of the characters, of the Virasoro characters under modular transformation. And these Ishibashi states, they are the solutions for the conformal boundary conditions, and they are just a linear combination of left and right linear combination of tensor product of left and right moving CFT states. This linear so the sum is in one Verma module, and then you sum up over the descendant levels and the states on a given descendant level. And then if you apply this Hamiltonian on this kind of states, so this kind of states which you form the linear combination, then it turns out to be diagonal. So in for every term in the linear combination, you're gonna have this expression for the ground state energy density. That you have to minimize this. So what you can do is you calculate this for every state in the linear combination, and then you pick the lowest one. So at the end, all but one alpha A is gonna be 0, and then at the end, the ansatz is only one regularized boundary state. Okay, and then so the aim of this talk is to verify this ansatz. So first, what you can do is you can take an integrable model when you have theoretical predictions for this ground state energy density. So if you take, for example, this series of integrable models, this E8, E7, E6 scattering theories, which are perturbations of the tricritical Ising model, the Ising model, the tricritical Ising model, and the tricritical Potts model with very specific perturbations, which are all very relevant. In this case, there are formulas in the literature, this paper by Fatyayev, that you can calculate the relation between the mass, the masses of the theory, and this coupling that you add in the Hamiltonian, and also you can calculate the back energy constants. So if you set the lowest mass in the theory to 1, this sets your scale, and then in this case, like the exact result says these numbers for the ground state energy density, and Cardy's ansatz say these numbers. So if you so you can see that in these cases the ansatz is quite reasonable. But then you might think that maybe it's related to integrability or something like this. But Cardy's ansatz doesn't suppose any integrability or whatsoever. So what you can do is take a non-integrable model. For example, I pick this perturbation of the tricritical Ising model with this 3/80 perturbation, and then this is the ground state energy against the system size. So you can see the line is just the ground state energy density given by Cardy's ansatz times the volume, and these dots are numerical results, which I'm gonna show you later how to get these points. So you see, even in the non-integrable case, the ansatz gives the right ground state energy density. Okay, so this is all very nice, but we still don't know anything about like the state itself. We don't know if it's a good ground state or it's just something. So I'm gonna use this left-right entanglement entropy to answer this question. So first of all, I would like to give some context. So first, this left-right entanglement entropy, which is the entanglement between left and right moving CFT modes. So this first appeared in the work of Leon Hardane and Ki Katsura Ludwig, where they studied topological gap topological states of matter in 2+1D. And what they did, you have your 2+1-dimensional system. Let's say you have a ball, and then you cut it to 2 halves. And then you can calculate the entanglement entropy between the 2 halves. And this is called topological entropy. And these topological phases, these topological states, when you define them with some boundary, then it turns out that they possess edge states, and they can be described by chiral CFT, let's say left or right moving CFT on the boundary. And what they found is that the reduced density matrix for this kind of cut, when you cut the topological state to 2 halves, the reduced density matrix is the same as the thermal density matrix of the chiral CFT which lives on the boundary. And there is a possible interpretation of this. So when you cut it to 2 halves, then you have 2 edges. And then you can say that left-moving CFT excitations live on one edge, and right-moving excitations live on the other edge. And then what they say, then the entropy between the 2 halves is nothing else, just the entropy between the left movers on one edge and the right movers on the other edge. So this was the context when this left-right entanglement entropy first appeared. And then there were some calculations by string theorists for many different cases. But then there is this recent results for regularized boundary states of CFTs. So in this paper from 2015, Das and Datta, they studied this kind of states. So you take some linear combination of Ishibashi states that I defined earlier, and then you can take any linear combination of them. And this state by itself is a non-normalizable state, so they can put some regularization factor here, and there is a normalization which is related to the Virasoro characters evaluated in a specific point. So these are the states that they studied. So remembering that the Ishibashi states are of this form, so tensor products of linear combinations of tensor product of left and right movers, you can take the partial trace, let's say over the left movers, the right movers, and you end up with let's say the reduced density matrix of the left movers, and this is the expression what you get, where this sum runs over the primaries in the CFT and also the levels at the given modules, like in the Ishibashi state. So again, if you treat this in large volumes, let's say this L over tau is big, then and the calculation, what they did is calculating powers of the reduced density matrix. So basically what they calculated is the general Rényi entropy, and using this large L expansion and modular invariance, they ended up with this result for the von Neumann entropy. So as you can see, there is a non-universal term which depends on this regularization parameter in the state, and it's linear with the system size, and also the central charge of the CFT appears. And there are these universal terms which only depend on the coefficients in the linear combination and the modular matrix elements. And then when you choose this boundary state to be a specific boundary state, namely a physical boundary state, then this psi, you know that this can be written in terms of the modular matrix elements, and the expression simplifies to this. So there is the non-universal term, which scales linearly with the system size, and there is a universal term which only depends on CFT data, basically. And then if you remember what was the ansatz of Cardy's, it's exactly this form. It's some regularized physical boundary state. So like if this is true, when you take the ansatz from Cardy, and you calculate, when you get the ground state somehow of a massive field theory, and you calculate this left-right entanglement entropy, then it should give this formula. Okay? And now I'm going to show you how to get this information about the states, which is going to be the numerical part of the story. So I'm going to introduce this truncated conformal space approach. Okay, so this approach was developed by Yuval Zamolodchikov in 1990, and they used it to calculate the finite size spectrum of the scaling Lie-Yang model. And after that, it appeared in many different versions and with many different names, like Hamiltonian truncation, truncated Hamiltonian, truncated space, truncated conformal space, blah 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 approach. But the idea is very simple. So you take this type of Hamiltonian, which acts on an infinite dimensional Hilbert space, but discrete one, and then you can write it in this form. Like there is an H0 and some perturbation, and the H0, the spectrum of H0 is well known, and by well known I mean you know the eigenstates, you know the eigenenergies, but on the top of that, you can calculate any matrix elements of any operators in this basis. Okay, so if you have this V, then on this the eigen basis of H0, you can calculate the matrix elements of your perturbation. But this is still an infinite dimensional problem, so you cannot really do anything with this. But what you can do is to take some projector to a low energy subspace of this H0. Let's say the energy is smaller than a cutoff, and then you project your Hamiltonian to this subspace, and this subspace now is finite dimensional, and then based on this you can calculate any matrix elements of this matrix, and then you just numerically diagonalize it, and then you can see like increasing the cutoff how things work, like and then actually when the matrix elements between low energy states and very high energy states which you exclude, they are very small, then at least the low energy spectrum can be extracted very, very accurately. Okay. So this is the numerical approach that I'm using. And this approach was applied for many different things. Like as I told you, like in integrable theories, you can get the spectrum and the scattering phases exactly, and these were actually verified by this truncated conformal space approach. Also, form factors can be extracted. Recently, people studied correlation functions, and also quantum quenches and time evolution can be studied, because what you can do is you do the time evolution numerically on this truncated subspace, and there are recent works on this. And then, so this is related to dynamics and maybe transport at some point. These two, correlation functions and time evolution. And then also real space secondary entropy can be extracted. And as I told you, that everything depends on the cutoff. So when you increase your cutoff, then the results might converge to the exact value or not converge at all, or can be many scenarios. But when they converge, but converge very slowly, then you would need like very big matrix, which you cannot really handle. But there are some renormalization group improvements where you can say something about the infinite cutoff based on I think the battery died. No. It's back. Okay. Okay. But all these applications were about 1+1 dimensional theories. Recently, Slava Rychkov and his collaborators, they extended to solving some problems in higher dimensions, and there is a lot of work on it actually right now. If you're interested in some details, there is a nice review from 2017 from James Koenig, Lechemin, and Robinson and Zwelik, if you're interested in this approach. So let's use this, let's specify this H0. This here. So I'm gonna use the conformal Hamiltonian for this because I'm studying perturbations of conformal field theories. So if you take the diagonal modular invariant of the CFT, then the Hilbert space is the sum over tensor product of left and right Virasoro modules, and the sum runs over all the fields in the Katz table. But you can embed this like generally in some Hilbert space, which can be written as a tensor product of left movers and right movers. Okay. So as I told you, in CFT, you know a lot, so you can generate all the states, all the eigenstates of the CFT Hamiltonian, and using conformal word identities, you can calculate any matrix elements of any operators that you want. So if you have a Hamiltonian which is a perturbation of CFT, then you can set up this this truncation method. And it's also just to mention that we are using periodic boundary conditions and spinless perturbations, so it helps you a lot because you only have to consider like distinct momentum sectors. You don't need to keep all the states, which you can in principle have. You can go to different momentum sectors and see only one of them. For example, if you are interested in the ground state, that must be in the total momentum zero sector. And also I mentioned this convergence properties. So in this case, the convergence depends on the conformal weight of the perturbation. So the more relevant the perturbation, the more convergent the approach is. Like in the first application, Yurov and Zamolodchikov, they used 16 states, and they get very, very accurate result for the scaling Liang model. Just to show you an example, like what is the general outcome of this approach? Like the first outcome is the picture that I showed you before, the ground state energy against the system size. And here in this picture, I took the E8 scattering theory, and I plotted the relative energies, like the energy of the state minus the energy of the ground state. So what you can see here is the gap of the theory. So this is volume. Here you can see finite size effect, but in large volumes you can read off the gaps. And these lines are calculated from integrability. So in this theory, actually, there are 8 particles. These are the masses of the first 3 one. And this picture I generated with 500, more or less like 500 states. And then you can see that it's very accurately gives back the first 3 masses in the theory. But when you do the diagonalization of this Hamiltonian, you not just get the eigen energies, you also get the linear combination for the vectors. So let's say the ground state can be written in this form, like some linear combination of tensor product of left and right movers, and then these these numbers here, the CLR, they are just numerical numbers which are the outcome of the diagonalization process. But once you have this, you can easily calculate any matrix element of the density matrix, and then you can carry out very, very easily the trace over the right movers, for example, and then you can have the reduced density matrix of the ground state with respect to this left-right separation. Just to remind you, the ansatz, Cardy's ansatz, was of this form. So it's a regularized boundary state. And as I told you, there is only one term in the linear combination. And there is this tau which you extract from the minimization principle. And the results of Das and Datta, they are actually for this type of states. So what you can do is from the minimization process, you get the tau, and then you just plug back in the formula for the left-right entanglement entropy for this special boundary states. And then you can match this prediction with the predictions from the numerics. And this is what you get. So this is the left-right entanglement from for the E8 scattering theory. Here I put different lowest masses, so I can play with the scale. Like these are for lowest masses being 0.0, 0.5, 1, and 2. And then you can see that these lines are from this formula. And then you can see that there is a linear term which is non-universal. It depends on this tau. And this tau, it depends on the mass of the theory, because for different couplings, you have different solutions for the minimization. But you can see that the universal term is the same for all of them. So it's really universal. Just to give you another example, which is non-integrable, this that I mentioned before, this tricriticalizing model plus this particular perturbation. In this case, there is no mass coupling, exact mass coupling relation, so I just set the coupling to some given number, and this is what you get. So here you also can see that there is a constant and the linear slope, which is governed by this tau in the exponent. Actually, I'm about to produce more plots to see the universality in these other cases as well. So this constant here. And this is really the same for anything. And okay, you can see that these dots actually they go to 0, but both Cardy's ansatz and both the results of Das and Datta for the left-right entanglement entropy, they are valid in large system sizes. Okay. And then it's clear if so this 0 volume is basically the fixed point, is the UV fixed point. And in that case, the CFT ground state is just one single product states of the left moving CFT ground state and the right moving CFT ground state. So the left-right entanglement entropy of that is 0. But actually, you can go deeper, because you also have the exact form of the reduced density matrix. So from this, you can read of this left-right entanglement spectrum. So basically, you take the logarithm, and then this is what you get. So there are the logarithm of the coefficients in the linear combination, which are in our case just some modular matrix elements. And there are these other factors. So these H, A, and N, they are like the different conformal weights in the CFT, and N are the different levels. So if you plot, you can calculate this as well from the numerics, because you have the numbers in the linear combinations, and then you can just plot them together. So these are the first 6 eigenenergies of this entanglement spectrum, of this entanglement Hamiltonian, this left-right entanglement Hamiltonian. So this first one, so this one here, this is related to the identity module. This next one is related to the module of 1/16 at level 0. This next one is related to the module of conformal weight 1/2, because this is okay. This is E8 model, so this is the perturbation of the Ising fixed point. And in this case, you have 3 operators: the identity, the magnetic field, and the energy density. And they have 0, 1/16, and 1/2 conformal weights. And this next one is actually the first descendant of the magnetic field, because you don't have first descendant for the identity operator. And this is the first descendant of the energy density. This is the second descendant of the identity, and so on. So you can see that the dots coming from the TCSA at large volumes, they really converge to these lines that are predicted by Das and Datta result. Okay. So after this, let me conclude. So what we have seen is that Cardy's ansatz for ground states of massive perturbations of conformal field theories. They capture very well the energy density of the ground state, and also capture very well the left-right entanglement entropy of this ground state, at least for very relevant perturbations. Because the two examples that I showed you, they both are very, very relevant perturbations. So one was 1/16, and the other one's 3/80. So it's very relevant. And we also saw that not just the left-right entanglement entropy, but the left-right entanglement spectrum also matches very well. And this is a new application of the truncation method. And here I just want to mention that if you use perturbations which are not so relevant, like close to 1/2, for example, then the results are not so impressive. I just didn't show you. But because we still don't understand what's happening there. We don't know if we have to use more states in the truncated conformal space approach, or we have to implement the renormalization procedure, or the ansatz itself is getting worse when the perturbation is less relevant. So we have to see what's the answer for this question. And also what I want to do is calculating the time evolution of this type. So for example, you can start from the ground state of the CFT, and then you can apply numerically, you can apply the time evolution with the perturbed Hamiltonian, and then you can see like this would be like some global quench, and then you can see how the left-right entanglement entropy was after a global quench. And it would be very nice if this kind of thing can be calculated from other approaches, like from chains or whatsoever, because this entanglement entropy is very specific. People usually do space-like separation, but this is the separation based on left and right moving conformal modes, which is somewhat unusual, but we can see that it's useful. So that's it. Thank you.
Okay, thank you for your talk. Questions?
So from the entanglement Hamiltonian, I should be able to see the what you call entanglement spectrum, right? So
Yes, yes.
So if I look at the formula, for example,
Yeah.
one of the last formula, what would be entanglement spectrum? Is it just I should select some values for the representations or something like that in the model matrix, or what defines? Or I should solve the problem of the diagonalizing this Hamiltonian.
Okay. So so what you do is you calculate the reduced density matrix from this, which is also a numerical matrix based on the coefficients in the linear combination which you extract from the diagonalization of the Hamiltonian. And then you have this reduced density matrix, which is also a numerical matrix, and then you diagonalize it again.
And what's the relation of this entanglement spectrum with the original problem? These eigenvalues, are they related to any characteristics?
So it's basically
related
related through the ansatz, because the ansatz says that the ground state is a regularized boundary state. And then you have the result from for entanglement spectrum and reduced density matrix and entanglement spectrum for these specific states. So this so you put these two together and you have some result. And then you can check it numerically if it's true or not. And then it seems like in large volumes, the dots which are from the numerics, they really converge to the lines which are calculated from Cardy's ansatz combined with the result for the specific case. So it really shows you that the state itself is at least very close to the proper ground state.
Okay, any further questions? If that's not the case, let's
Thank you.
thank